Today we are going to learn about the remaining applications of Gauss law. Yesterday we have learned the 3 applications of Gauss law. We are trying to find out electric field intensity from different kind of charges, line charge distribution or a plane sheet or a sphere. So today we are going to learn electric field intensity due to a thin infinite plane sheet of charge. So what we will do is, firstly we will consider a thin infinite and plane sheet of charge. Okay, so we have given some charge, let us say Q, with surface charge density sigma. So now our idea is to find out electric field intensity at this point P, which is at a distance R. See, from here you want to find out. So using Gauss law, first what we are doing generally, we are considering a surface. We are considering a Gaussian surface, and then we are trying to find out the flux passing through it. Based on that, we are trying to find out the electric field intensity. So what we will do here, we will consider a uniform cylindrical Gaussian surface. Its length is 2r, r plus r, 2r, having a cross section of ds. Right? So let us say this is a point P. Exactly the end of the cylinder is passing through this point P. So this cylinder have 2 surfaces. One is the curved surface, the other part is the 2 ends or the edges of the cylinder, that is P and Q. So first what we will try to do, we will try to understand how much flux is coming out of this closed cylinder, right? So we know that flux is generally given by integral E dot ds. Okay, but here you can see flux is contributed by curved surface as well as the ends. So I'll write this as ends plus curved surface area. Right. Now, because of what is the contribution of ends, we will see first. You can see here electric field intensity is directing outwards perpendicularly to the plane sheet. So it is directed in this way, and the area vector of this end is also acting in this direction. The angle between both of them is 0. So I'll write here EDS cos, I'll write 0 plus, now you can see angle here for curved surface. The area vector is acting in this direction, electric field intensity is acting in this direction or either this direction. So what is the angle? It's 90 degrees. So here it is EDS cos 90. We know cos 90 value is 0. So the contribution of curved surface is nullified here. So we are left out with this, that is integral of E ds. Cos 0 value is 1. Okay, right. Now we will see, we know that this value is nothing but Q by epsilon naught. Q by epsilon naught. The total flux which is coming out, it is Q by epsilon naught. And let me tell you that, friends, electric field intensity at a distance r is same wherever you select, whether you select the point here or here or here, everywhere electric field intensity is same if the distance is exactly r. So that is constant. So I'll bring this E out of this integration, then it becomes E integral ds. So the area which I have taken is just only ds here. So here I can write then I have defined earlier that surface, it is having a surface charge density sigma. So sigma is given by charge by area. Area is ds, right? So let us substitute the value of q here. Q is equal to sigma ds. So sigma ds by epsilon naught is equal to EDS, because this is nothing but the integration of ds is nothing but the area which we are considering, right? But let me tell you, there are two ends which is contributing the flux. So let us write 2, because there are two ends. This is for one end. For two ends it will be 2 EDS. ds cancel. So E is given as sigma by 2 epsilon naught. So friends, this is the electric field intensity at a point P, which is located at a distance r. So it's very clear that the electric field intensity is not depending on the distance of the point located from the thin sheet. It is depending on the surface charge density, right? If these two are constant, then obviously electric field intensity also will be a constant, right? Friends, let us say the thin sheet which we are considering, let us say it is slightly thick and it is having uniform thickness. In that case, it have two surfaces. This is one surface and we can see this is the second surface. But as I told you, this is uniformly charged, having uniform charge surface charge density. So in that case, charge will be distributed both the sides equally. And let me tell you, for both sides, electric field intensity is exactly perpendicular to the area. So you can see here, due to the first surface, electric field intensity is acting in this direction. Due to second side also, the electric field intensity is acting in this direction, because if you have a positive charge here or here, it doesn't matter, it will be radially outwards. So if we consider a point here and we are trying to find out the electric field intensity because of this thick sheet of infinite uniform charge density, in that case I have to consider superposition principle of electric field intensity at this point. So we can take the resultant will be E1 plus E2. Going with the value which we have derived earlier, for E1 it is sigma by 2 epsilon naught, and for E2 also we'll go with sigma by 2 epsilon naught. So on adding we will get 2 sigma by 2 epsilon naught. To it cancel, you get sigma by epsilon naught. So this is the resultant electric field intensity at this point due to a thick infinite sheet of uniform surface charge density, right? Friends, now we will learn the last application of Gauss law. Electric field intensity due to two thin infinite parallel sheets of charge. You can see here in the picture we have two thin infinite parallel sheets of charge A and B. Let us say the surface charge density on this is sigma 1 and on this sheet surface charge density is sigma 2. And then let us assume that sigma 1 is slightly greater than sigma 2 and this is greater than 0, right? Now our idea is we'll try to understand electric field intensity in these three regions, region 1, region 2, region 3. Here if you look at this region, electric field intensity due to this is E1 and due to the second one is also acting in this direction, right? Both are acting in this direction. If I calculate the electric field intensity in the region 1, so it is what we will do to calculate, we will consider left side as negative and right side as positive. Both are acting left side, so it will be minus E1 minus E2. So considering the previous results of electric field intensity at a point due to a thin infinite sheet of charge, at this point it will be minus sigma by 2 epsilon naught sigma 1 sigma 2 2 epsilon naught. So here I will write 2 epsilon naught, will take common, sigma 1 as sigma 2. So this is the resultant electric field intensity in region 1 due to these two thin sheets of parallel sheets of charge. Now we will try to calculate electric field intensity in the second region. So here you can see, if we consider a point somewhere at the center, electric field intensity due to the second sheet will be acting in this direction and E1 in this direction. So E1 minus E2. E1 is sigma by 2 epsilon naught minus sigma 2 by 2 epsilon naught. So it is 1 by 2 epsilon naught sigma 1 minus sigma 2. If we consider electric field intensity at a point outside this and the region 3, so it will be E1 plus E2, because both E1 and E2 are acting in this direction, which is nothing but positive. So we are going to get right. So this is the resultant value. Right. So I am going to tell here one exceptional case. In case if surface charge density are equal and opposite, in that case we have very different results here. Let us say here we can see the case where one sheet is having positive charge, so that is plus sigma, and here it is minus sigma. In this case, then we will see the result here. At E1 it will be 0, because 1 by 2 epsilon naught, sigma 1 value is sigma and sigma 2 value is minus sigma. So you can see here it is 0. So here electric field intensity is 0. And here if we consider in the third region, there also it is 1 by 2 epsilon naught sigma plus minus sigma. Here also it is nothing but 0. So here also electric field intensity is 0. Here the electric field intensity will be 1 by 2 epsilon naught sigma plus sigma. Okay, so sigma 1 is sigma and sigma 2 is minus sigma. So minus and minus, because you can see the result here, sigma 1 minus sigma 2. Here it is sigma minus of minus sigma, it becomes plus sigma. So it is 2 sigma by 2 epsilon naught. 2 get cancelled. So we are left out with sigma by epsilon naught. So it's very clear that between these two plane sheet of opposite charges, there is some uniform electric field. So that is given by sigma by epsilon naught. And let me tell you that practically this is the way they produce uniform electric fields also. Right? I hope you understood. Friends, in this problem, they gave that this is an electric field and there are 2 points A and B. In the question they told that the electric field line separation at point A is half of the electric field line separation at point B. And they also gave that electric field at point A 60 Newton per Coulomb. So they asked us to find out two things. One is electric field at point P, and they also asked us to find out what is the force experienced by a proton which is placed somewhere at point P. So let us first calculate the electric field at point P. So from the given condition, clearly you can identify here electric field is more and here it is less because the segregation of a congregation of lines is more here and it is very less. So I would say that E B is EA by 2. So EA is given, EB is equal to 60 by 2. So answer is 30 Newton per coulomb. So we have found out the first answer. Second one, what is the force experienced by a charge? It is nothing but it is EQ. Electric field is given 30 and charge of a proton is 1.6 into 10 to the power of minus 19. So you are getting around some 4.8 into 10 to the power of minus 18 Newton. So this is the force experienced by the proton. In this problem, they are asking us to find out VA minus VB is equal to, is it positive or is it negative or is it zero? That is, and there are two cases. If Q is positive, then is it positive or negative? If Q is negative, is it positive or negative? VA minus VB. So from the picture it is very clear that OA is less than OB. Okay, this is one thing is clear. OA is, so this is less than OB. Okay. Now first we'll try to find out VA minus VB value. VA minus VB, potential at A minus potential at B. From the definition, from the formula, we can write it's 1 by 4 pi epsilon naught. It's Q by OA minus 1 by 4 pi epsilon naught Q by OB. Well, a common 1 by 4 pi epsilon naught 1 by OA minus 1 by OB. Since OA is less than OB, 1 by OA can write 1 by OA is greater than 1 by OB, which means that this entire quantity is positive because this is greater than, this is less than this. So this is positive. So VA minus VB is positive. Now Q value is here. So if Q is positive, so we got to answer if Q is positive, in that case VA minus VB is also positive. If Q is negative, if this is negative, then this entire thing also becomes negative. VA minus VB is negative. Right, hope you understood this. Friends, in this problem, they gave us some conditions, 3 questions. Conditions are, let us imagine a right circular cylinder. Right. So they gave us the condition that if we imagine x-axis and y-axis, let us say This is the x-axis and this is the y-axis, right? At the midpoint, the length of this cylinder is around 20 centimeter and the radius of the cylinder is 5 centimeter, right? So this length will be 10 centimeter. It's very clear that x greater than 0, the electric field will be 200 I Newton per Coulomb. So what we are supposed to find out? This is one face of the cylinder, right, circular cylinder, and this is one side. We are supposed to find out net outward flux through each flat face. So we have to find out flux through each flat face. Here we can see the electric field intensity is acting outwards, and this is the area vector acting in right side. Here the electric field will be given as minus 200 I, so it is E, and this is the direction of the area vector, right? First we start with left face. Flux through left face. So phi, we can write this as delta S, right? So surface area, it is pi, this is a circle, r square minus I cap, direction. R value is 5 centimeter. It can be written as 0.05 whole square minus I cap, right? So E value is given 200 I. Here it is minus 200 I. So you can write here minus 200 I cap, and delta S is pi 0.05 whole square minus I cap. Right. So on solving this, you would get somewhere around 1.57 Newton meter square per Coulomb. So this is the value left face, flux through left face. Similarly, for right face also, we get, if we solve all that, we would get around 1.57 Newton meter square per Coulomb. Second one, we are supposed to find out net outward flux through cylinder, entire cylinder. Now in entire cylinder we have these two faces as well as the curved surface. So if you look at curved surface, the area vector is acting in this direction and electric field is acting in this direction. You can see the angle is 90 degrees. So if we are trying to find out flux through curved surface, so that is E cos 90, which is nothing but 0. So contribution due to the curved surface, contribution towards flux through the curved surface will be 0. So net flux will be equal to flux through left face, flux through right face, plus flux through curved surface. So this is 0. So we get 1.57 plus 1.57. We get totally 3.14 Newton meter square per Coulomb. So this is the total flux. Now we'll solve the third one. Net charge inside the cylinder. So we know flux is given by Q by epsilon naught. Okay, so this is the net flux. So Q is equal to net flux into epsilon naught. So net flux is value is 3.14. 8.85 into 10 to the power of minus 12. An answer of 2.78 into 10 to the power of minus 11. It's Coulomb. Friends, in this sum, they are given the dielectric constant for water is 40. We are supposed to find out the electrical permittivity in the water. So we know that dielectric constant is given by electrical permittivity in the medium to electrical permittivity in vacuum. So EW is equal to A E naught epsilon naught. So dielectric constant is given 40. Epsilon naught value is 8.85 into 10 to the power of minus 12. (354) or we can write this as 3.54 into minus 10 coulomb square meter square. Friends, in this question they gave a dipole to us. The locations of dipoles are on z-axis. One charge, that is 2.5 into 10 to the power of minus 7 coulomb, is at coordinates minus 15 centimeter on z-axis, and there is one more charge minus 2.5 into 10 to the power of minus 7 coulomb, that is second charge QB, on positive z-axis. The location is 0, 0, 15 centimeter. So the distance between these two is 30 centimeter. So this value will be 30 centimeter, or we can write this as 0.3 meter. Okay, this much is clear. What they're asking us? They're asking us to find out the dipole moment, the torque acting on this dipole, because this dipole is placed in an electric field of 5 into 10 to the power of 4 Newton per coulomb, which is at an angle 30 degrees to z-axis. So it will experience a torque. We got to find out the torque, right? So now we will first find out the dipole moment. We know that P is equal to 2AQ. 2A value is given 0.3 and Q value is 2.5 into 10 to the power of minus 7. So you are getting around 7.5 meter. So this is the value for dipole moment. Next we got to find out torque. Torque is equal to PE sine theta. Okay, P value is given 7.5 into 10 to the power of minus 8. E value is given 5 into 10 to the power of 4 and sine 30. So we are getting 37.5 into 10 to the power of minus 4, and sine 30 value is 18.75 into 10 to the power of minus 4 Newton meter. So this is the value of the torque. Friends, in this question they asked us, inside a cube they place the charge Q naught. What is the flux which is emanating outside through two opposite phases? So to answer this, firstly, what is the flux generally coming out of this cube we have to answer. So we know the total flux coming out is Q by epsilon naught, right? This is the total flux, electric flux emanating out of this cube. But we have to find out what is the flux passing through two opposite phases of this cube. So So what I would do is flux emanating from each phase, from one phase, is nothing but 1 by 6 times of Q by epsilon naught. Let me tell you that cube have 6 phases. Flux emanating from each phase will be 1 by 6 of the total flux, that is Q by epsilon naught. Then from flux from two sides, two phases, two opposite phases will be 2 by 6 Q by epsilon naught. So it is Q by 3 epsilon naught. Next we will see in this question they said that there is a hollow charged sphere whose radius is 5 centimeter. At a distance of 15 centimeter, 20 centimeter, the potential is 15 volts. Then what is the potential inside this sphere? That's the question. So here I have to remind you all that the potential inside is equal to potential on the surface. So if we find the potential on the surface, that itself is the answer. That is the potential inside the charged sphere. So we know that V is given by 1 by 4 pi epsilon naught Q by R, where V is inversely proportional to R. So we try to find out the potential at the surface. We'll take the ratio V20 by V5 is equal to R5 by R20. So potential at a distance 20 centimeter away is given as 15 volts given in the question. So 15 by potential on the surface is equal to, this is 5 centimeter and this is 20. So we are getting around 60 volts. So the potential inside the sphere is equal to potential on surface. So potential inside is equal to 60 volts. 60 volts is the answer. Friends, in this question they have given us cesium chloride crystal. They are asking us to find out what is the electric field intensity somewhere here at chlorine ion. Generally in cesium chloride ion, in this arrangement, 8 cesium ions, they surround 1 chlorine ion. So in the question they are given cesium atom is generally having a deficit of electron, and chlorine atom is having a gain of electron. It is having some excess electron. So this is a negative charge and these are positive charges. So first part is we have to find out what is the electric field at chlorine ion. So that we have to find out. It's very clear, this is a cube structure. So here the electric field is because of all the 8 cesium atoms. So all these 8 atoms, according to the symmetry, the electric field cancel out at this point, because the force here is cancelling out, because we know E is equal to F by Q, right? So here the net force is 0 because of symmetry. Okay, so here for example the force experienced by chlorine, due to this one is acting in this direction, and due to this it is acting in this direction, and the distance is also same, so the force cancel out. Similarly this ion and this ion, they cancel out their forces on chlorine, so the net force will be 0. So the net electric field is 0 at the chlorine ion. The second part in the question is They asked us to find out what is the electric field on chlorine if the atom at point A is taken out. Then what? Then there will be a force due to this atom on chlorine ion. Okay. In that case, we will find force is equal to 1 by 4 pi epsilon naught q square by r square. Okay. So we got to find out the distance between chlorine and we have to find out this r value. So in a cube, this is given by formula r is equal to root over 3. Okay. It is x by 2 whole square. Okay. So here x is the side of cube. Okay. So finding out that r is equal to root over 3, it is 0.40 nanometer. So it is 0.20 whole square 10 to the power of 9 minus 9 meter. So we are getting a value around 0.346 into 10 to the power of minus 9 meter. Right. So this is the R value. Now we will substitute the value of 1 by 4 pi epsilon naught is 9 into 10 to the power of 9 into q square. Q value is 1.6 into 10 to the power of minus 19. We are considering an electron's value here. Square by r square 0.346 into 10 to the power of minus 9 meter whole square. So we are getting around 1.92 into 10 to the power of minus 9 Newton. So this is the net force acting on the chlorine due to this atom when this is removed. Remaining atoms which are present diagonally, their force get cancelled out.